Welcome to the deep dive. Today we're jumping into something pretty fascinating, quantum computing. These quantum machines, they promise so much, right? Solving problems regular computers just can't touch. But there's this persistent problem. They're incredibly fragile. The basic units, the qubits, they're super sensitive. Noise, temperature, tiny disturbances, it all causes errors. And these errors pile up really fast, making it a huge challenge to build practical quantum computers.
It's a major roadblock, absolutely. Keeping those quantum states stable long enough to compute anything meaningful is tricky.
So one of the really promising ideas to fix this is something called topological quantum computing.
That's right. The idea is to encode the quantum information differently.
How so?
By embedding it in the geometric properties, the topology of these exotic particles called anyons.
Anyons. Not your everyday electrons or photons, then.
No, definitely not. They're quasi-particles, predicted to show up in certain, flat, two-dimensional materials. And the hope is they offer much better protection against noise.
Okay, that sounds promising. But there's a catch, isn't there? That leads us to our big question for today. How do we get from the sort of partial power these systems might offer now to the full universal quantum computation needed for those, world-changing applications?
Well, and this is where it gets really interesting. The answer seems to involve a particle that honestly was kind of ignored for decades.
Okay.
We're going to look at how some pretty abstract math suddenly pointed towards this lost particle that might just change the game entirely.
A lost particle. Okay, I'm hooked. So let's start with the current best bet. You mentioned anyons, specifically Ising anyons.
Exactly. Ising anyons are probably the most studied candidates right now. You find research focusing on them in systems like the fractional quantum Hall effect or topological superconductors.
Right, those are familiar terms in the field. And how do scientists actually, use these Ising anyons to compute?
They perform operations by doing something called braiding.
Braiding, actually weaving them together.
Pretty much. Imagine physically moving these particles around one another in specific patterns. Think of it like braiding strands of hair.
Okay.
This braiding action corresponds to performing certain quantum logic gates, specifically a set known as Clifford gates.
Clifford gates. Now, I know those are useful, but they're limited, right? That partial toolkit you mentioned.
Precisely. Clifford gates are powerful for some things, but they are not sufficient for universal quantum computation. You can't run every possible quantum algorithm with just those.
And that's the gap, the universality gap, the thing researchers have been trying to figure out how to cross.
That's been the puzzle, yeah. How do you get beyond Clifford gates in these topological systems?
Yeah.
And this brings us to the surprising discovery. The answer seems to lie with this particle that was essentially dismissed. Researchers have now called it the neglectin.
The neglectin. That's a fantastic name.
Yeah.
Because it was neglected.
Literally written off as irrelevant in the standard theoretical frameworks. Just didn't seem to do anything useful.
Okay, so what's the secret? How does this previously ignored neglectin suddenly bridge that universality gap?
Well, the beauty of it is its simplicity. You apparently only need one neglectin.
Just one.
Just one. And here's the real kicker. It doesn't even need to move. It's stationary.
Wait, it just sits there? How does that help?
The computation happens when you braid the Ising anyons around this stationary neglectin. That interaction, braiding around the neglectin, is what provides the missing operations needed for universality.
Wow. Okay, that's counterintuitive. A particle that does nothing but sit still unlocks universal computation just by having others move around it. Could this seemingly simple addition really be the future pathway? It feels almost too elegant.
It's definitely a paradigm shift, and its origins are just as surprising. It comes out of a new mathematical approach, a framework called non-semi-simple topological quantum field theories, or TQFTs for short.
Okay, hold on. Non-semi-simple TQFTs. That sounds pretty deep in the mathematical weeds. Can you give us the gist?
Yeah, it is a bit of a mouthful. Let's try. So, TQFTs generally are mathematical tools used to describe these topological systems. They focus on properties that don't change when you deform things like how things are connected, their topology.
Right, the braiding patterns, that kind of thing.
Exactly. Now, the non-semi-simple part is key here. In the more traditional standard TQFTs, certain mathematical objects were just thrown out. Discarded.
Why? What were these objects?
They were objects that had something called quantum trace zero. Basically, a mathematical calculation yielded zero, and the assumption was, well, these must correspond to states that aren't physically meaningful or carry no information. Junk data, essentially.
So standard practice was just to ignore them, tidy them out of the theory,
Pretty much, yeah. Cut them out to make the math cleaner, supposedly more physical.
and the neglectant was hiding in this mathematical drip job.
You got it. Aaron Lauda at USC, one of the researchers, put it really well. He said, these discarded objects were actually the treasure everyone had overlooked. By keeping these quantum trace zero objects in the theory, this non-semi-simple approach revealed their structure and out-popped the neglectin.
That's incredible. Mathematical trash turned into quantum treasure. It really shows how abstract math can suddenly hit real-world problems, doesn't it?
It's a beautiful example of that, yeah. But there was still a problem with this non-semi-simple framework itself.
Ah, okay. What was the catch this time?
A big one, actually. These theories fundamentally violate something called unitarity.
Unitarity. That sounds important in quantum mechanics. Doesn't that ensure probabilities behave correctly, like add up to 100%?
Exactly right. It's a cornerstone principle. Violating unitarity means the theory, taken at face value, doesn't conserve probability, which most physicists would say is a fatal flaw. You can't have probabilities going above 1 or below 0.
So, how did they salvage the idea? If the math framework is flawed, how can it lead to valid computation?
This is where Lauda's team got really clever. They figured out a way to essentially quarantine the problematic parts of the theory.
Quarantine them? How do you quarantine bad math?
Well, the strategy was to design the system so that all the crucial quantum information, the stuff you actually care about for the computation, stays within the well-behaved unitary parts of the theory. Lauda used a great analogy. He said, it's like building a house with unstable rooms, but ensuring all critical work takes place in the structurally sound areas.
I see. So you acknowledge the unstable bits exist in the theory, but you carefully design your computation, your encoding, to avoid relying on them. You keep the important stuff safe in the sound rooms.
Precisely. By creating encodings that effectively isolate these irregularities, they found a path to get valid unitary computation out of a framework that overall isn't strictly unitary.
That's a fascinating workaround. It makes you wonder, could similar strategies, sort of cording off theoretical problems, work in other areas where theories don't quite match reality yet?
It definitely opens up that line of thinking, and it really hammers home the main point here. Mathematical structures we dismissed can suddenly become crucial for major leaps forward, especially in quantum information.
It really is that link between pure math and practical potential that's so striking here. So what happens next? Where does the research go from this point?
Well, there are two main tracks now. On the theory side, the team is working on extending this mathematical framework, exploring different parameters, and digging deeper into exactly how unitarity plays out or doesn't in these non-semi-simple TQFTs.
Okay, refining the math. And on the practical side?
That's the big challenge for the experimentalists. First, they need to actually find or engineer a real-world material system where a stationary neglectin could physically exist.
Right, finding a home for it.
Exactly. And then they need to develop the techniques, the protocols to actually perform the braiding around it and control everything.
So confirming it experimentally and figuring out how to use it.
Yes. But what's got researchers really excited is that this approach potentially brings universal quantum computing closer, using particles, the Ising-Enions that we, already have a pretty good handle on how to create and manipulate.
We're not starting from scratch with completely new particles. We're adding one special stationary ingredient.
That's the idea. If they can successfully build a system with a realized neglectin in the lab, well, that could genuinely shift topological quantum computing from a beautiful theory into a practical reality.
What an amazing story. From discarded math to a potential key for universal quantum computation. This deep dive really highlights how science can take unexpected turns. It leaves you wondering, doesn't it? Have we been sort of circling around the solution for universal quantum computing all this time, maybe overlooking this one simple stationary particle that could unlock the whole thing? We hope this exploration gave you some real insight into this cutting-edge development. Thanks for joining us on The Deep Dive.